Hi everyone, next up we'll have Rohit Patel from Meta. Hope you enjoy it.
Hey guys, can everyone hear me? All good? Okay. Afternoon, it's nice to be here. I'm Rohit. I work on our Llama team in the GenAI at Meta. We spend most of our time trying to build Llama models before we open source them. And today I'm going to talk a little bit about GenAI, what it is, how language is generated, and how to evaluate the models. I'll try to leave as much time as possible towards the end for Q&As. Just so I'm not repeating myself, how many people here already have a sense of what deep learning is and how language is generated? Okay, that's a lot. Excellent. So we can go a little bit faster through the first few slides. But the point of these slides is just to make it baseline everyone and just to make sure that everyone is sort of fully aware how easy this is. Like this is a relatively not a very, this is not rocket science. Deep learning is actually easier, at least in concept. And so just so everyone feels encouraged and empowered to actually take this on and research in this area. Okay. Looks like I'm having trouble advancing my slides. Oh, perfect, it works. This is a little bit about me. I already talked about myself, so let's just get to it. Before we jump into it, here's a slide that talks a little bit about what are evaluations and why should we care about them. And I will spend a good amount of time in this talk talking about evaluations, what model evaluations are, what they mean, and how do we do them. But the crux of it is that models don't have a convex intelligence envelope, which means that they could be really good at some things and really not very good at some other things. And you'll have experienced this. This sort of like was something that occurred to me also when I had a personal use case. I had a physical calendar that I just wanted to count the number of brown lines. Those were the days I was traveling in the year or something like that. And it's not a very complicated task. I did not expect the models to do badly, and almost every model just did a very poor job of it. So when you have this sort of a convex intelligence envelope, you can rely, and this is the case with humans, you can rely on people being intelligent in one area or one thing to transfer to another. Not necessarily the case with AI models of today, or at least the large language models that we're used to. So what does that mean for us, for people who are trying to, and for people who are trying to use these models? It means that they have to be very careful to make sure that the intelligence transfers to their particular use case. So they have to build evals for their use case and make sure that the models work for them before they start using them. Otherwise, you're just going to have sort of a failed AI project or deployment. And so eval is sort of like a way to rank or score these models for their performance along any given dimension, right? Okay, so coming back to what is GenAI. First, what are neural networks? So neural networks are basically just things, they take in a bunch of numbers and they will give you outputs as numbers. There are absolutely no exceptions to this. There are no neural networks that are non-number based, right? Like they take in numbers, they give out numbers. And the trick is that you have to take the real world, interpret it in the form of numbers, or take the network outputs and interpret it in some form of real world outputs to actually make neural networks useful in reality. So here I have an example of a neural network that is trained, and actually if you put in the leaf and the flower, and what this neural network is trying to do is classify some data you have on two objects, red, green, blue, and volume, and it's trying to classify this into leaf and flower. And it's a very simple neural network. It has one deep layer, and here what we're doing is, we're lucky that the data we have is already numbers, so we're going to just put it in the network as is. But leaf and flower are not things that neural network can output. It can only output numbers. So we have to come up with a scheme to actually understand or make it output something that we will interpret as a leaf or a flower. In this case, let's go with a particular scheme, which is, let's say that I'm going to make the network output 2 numbers, and whichever number is higher is the network's guess. This is purely our interpretation. The network does not know what a leaf or a flower is. But now we have a network that is capable of classifying objects into these 2 things. So that's a very simple network with a very simple classification scheme that does classify something into a leaf and a flower. And the math is very straightforward. It's all on the screen, right? Like, so you can actually manually on paper run this neural network if you wanted to. And I encourage you to take, I've already put in, I think, the leaf example in the neurons. But if you put in the flower numbers, it will give you, and run all these calculations again, it will give you the output that the classification that it's a flower. And that's sort of broadly how it works. Very, very simplified view. But it sort of captures the 3 key pieces you need to build a neural network, which is an interpretation of the numbers. So you want to transfer or sort of convert your real world ideas or whatever it may be to numbers so that it can be fed to the network. And then you want to have a scheme that takes the network outputs and actually translates it back into the real world, right? Like, so that's an interpretation piece to make a working neural network that you need to decide on. There's this structure. So here we had very simple structure, no biases, no activation, none of that. But you have to come up with a structure. And then there are parameters. So here on each of the lines, I have numbers that I've written. I've already pre-trained this network. But where do these numbers come from, right? Like those are the parameters, and you need to come up with those numbers somehow to make this actually a useful network. Let's talk about the last part briefly. So how do I come up with the parameters? Coming up with the parameters is very easy conceptually, very hard in practice, but very easy conceptually. If I had a lot of data on RGB volume here, and I had what we call label data, which is I knew which ones were leaf and flowers, I would know which of these last 2 neurons I want to be higher. And what I can do is I can just, what we call initialize the network, put random parameters everywhere, and then do this calculation that we show here on the first slide, right? Like calculate all the neurons. The circles are, by the way, the neurons. The lines are the parameters. So calculate all the neurons going from left to the right, and that's called a forward pass of a neural network. And then you're going to get some 2 numbers in the last layer. And these things are called layers, by the way, right? Like the first column is the first layer, the middle layer, the last layer, the output layer. So you're going to get some numbers in the output layer. And they're not going to be numbers that you're going to want, because it's going to say flower when it's leaf and stuff like that. But what you can do is you can perturb all of your parameters a little bit and see in which direction do you get better numbers. And that perturbation can give you, now you can keep doing this repeatedly. You can keep moving the parameters in directions that you want to get the leaf and flower numbers you want. And that's like training the network. That isn't exactly gradient descent. There are, in gradient descent, you are actually able to mathematically calculate the gradient, which is not very hard. It's just really a differential of that thing. But that just gives you a sense of like how you train it. You just you start with random set of numbers and you keep moving them around till the network starts to predict, in most cases, leaf for the data that you've given it that was leaf, and most cases flower for the data that you've given it that was flower. And then the hope is that after you've done all of that with the label data, that when you will give it an unlabeled data where you don't know whether it's a leaf or a flower, that the network will do the right thing because it's been doing the right thing on the label data. So you can use this kind of a concept to build very cool things such as generative AI. Instead of leaf and flower, I can expand the output layer to 26 characters. And I can pretend that when the neural network outputs 26, the one that it says is the highest number is the actual output character that the neural network is giving me. Now the problem with characters is we don't have, the network can only take in numbers as inputs, right? So we don't have a very good way of putting them in. So let's come up with a way, like let's come up with the simplest, stupidest way we can think of. Let's just assign every character a number. A equals 1, B equals 2, and let's put it in. Now you have a neural network that is capable of taking in characters and outputting characters. Now you can train this neural network to actually complete sentences like, here I have Humpty Dumpty, or, a quick brown fox jumps over a lazy dog. And so you can train it to complete sentences, and it will do so. And that's how you get to like sort of a language model that is finishing sentences, right? Now this is gross oversimplification. In reality, you have something called tokens, and you're not actually predicting at character level. Actually, people have built very successful character level models, but they're not nearly as good as modern large language models, where your actually vocabulary is very large, and you predict tokens, you don't predict characters, and these are hundreds of thousands, or tens of thousands at least in most cases. In some cases, it's 100, 150,000 tokens. So your last layer, we've come a long way from leaf and flower. Your last layer, you're actually predicting 100,000 numbers, and whichever one of them is the highest, you're saying that's the word that the network is predicting next. Now, if you're paying attention closely, you will realize there is a problem. How do if I can only generate the next word, how do I get more out of it? And the way you do it is you generate the next one and you pretend that's your input data and you put it back in the network. That gives rise to another problem, which is if I put it back in the network and the network inputs are fixed in size, what do I do as the input size is growing, as my sentence is growing? And what you really do is you throw it away. This is what happens in the models today. And that's the length of the context window. If you're out of context, that data is discarded. Now, the modern networks do have very long context windows. Like the latest Llama model is 130 plus thousand tokens. So, you're not going to run out in your day-to-day, but you will eventually run out. Okay, so that was a quick premiere on how language is generated from these models, and let's now go into evaluating these models, which is kind of like, I think, the interesting part for a lot of people. So, as I mentioned earlier, eval is a way to rank or score AI models, and generally in evaluation, what you're trying to do is you're trying to figure out some sort of a latent value function. A mapping from the space of models, imagine you have all the models in the world, to which one is the best one, or how do you rank them in terms of like how good they're going to be for your particular use case. If you knew this mapping, life would be very easy, because you'd be able to then iterate on the set of models and find the best one and use it for your use case. But since this mapping is not known, what you're really trying to do when you're trying to build an eval is actually you're trying to approximate this mapping, assuming that there exists a latent mapping and you're trying to approximate it. So to approximate the mapping, you're going to need three key things. You're going to need a sample of input prompts, a scoring of prompt responses, and a metric. So imagine a scenario you're trying to implement AI in whatever situation you have in the real world. And we'll go over an example later about how this eval really applies to like a practical real world. You don't know which model is the best one. You don't know what set of weights are the best one, and you don't know how to improve the model. And an eval is basically what you're trying to do is you're trying to sample the world in which this model is going to operate, and you're going to say, if it works well on this sample, and then I'm going to assume that it works well in this space in general. This sample is very specific to this space, and that's really what you're trying to do with eval. So what you need to sample is you need some input prompts, which is specific to that space, and you need a way to rank the outputs. So you give the prompts or you give the questions to the model, you get the answers, and you need a way to rank them and be able to say that this was a better answer than this other one, or score them, right? Either is fine. And then you build a metric. Once you have all these ranks and scores, you combine it, and you get a single score, because we're humans. We like to have like clear numbers to understand this is X percentage, this is Y percentage, something easy to digest. I'm not going to go too much into types of evals for GenAI models, but basically there are 3 types: automated, judge-based, or human. Automated is when you are using statistical methods. Judge-based is when you're using another LLM to actually answer the question of which response is better. And human is like a person goes through the responses and says, this is a better response, this is a worse response, stuff like that. Automated is by far, in terms of compute, very popular because it is very fast and it is very consistent over time. Human Radar has other good properties, but much more expensive to run. Technical complexity, easier to run the Human Radar evals. Judge-based evals, slightly more complicated. Automated evals are the most complicated from a technical standpoint. Here's an example of an auto eval from an MMLU data set, which I guess a lot of you guys may have heard about. And the scoring of the response here is basically very simple in this particular case. You take the 4 options and you take the log likelihood. So imagine you have the output layer and you have all the probabilities of each of the tokens in the output layer, right? Like the 100,000 or so. And what you can do is, with these probabilities, you can calculate the log likelihood of each of these options that are being presented to the model. So you're not even asking the model to answer the question. You're just calculating which answer coming out of the model has the highest probability. And that's sort of how MMLU works. And that way if you have, like this data set has 14,000 questions. So if you have 14,000 questions, you can get good tight confidence intervals, and you can be sure that you understand how the model is performing on this data set. Every time we release a Llama model, we release a lot of evals with each of the model release. This is just a screenshot of one of the paper tables that I spent, countless hours working on. And it talks about, Llama 3.1, how it performs on various benchmarks, and so on and so forth. Running good evals can be very complicated. It's funny because on the surface, the idea is actually not very complex, but it's the same thing conceptually. Neither is deep learning. But then in practice, you're trying to do so much optimization, and you're operating at very low precision levels oftentimes, that even the architecture of the GPU can make a difference. So whether you're on Ada or Hopper or something else, and in what precision is the reduce operations happening inside the GPU is going to make a difference in how you're going to see your results. Having said that, all of these differences are a nuisance, but even if you account for all these variations, and you can reduce all these variations, by the way, by fixing your architectures, by fixing your seeds, by fixing your batch sizes, and a lot of different things. And there are a large number of hyperparameters, so you can fix all of them and you can reduce them. But even if you didn't really do a particularly good job of it, a well-built eval will give you a tight enough variance and confidence interval that you're going to be in a good place. So let's talk about what evals could look like for some real-world examples, which is, I think, maybe more relevant to people here, especially if they're going to go and pursue something like this, and someone is going to ask you the question, how are you going to know that the AI is going to be good? So let's say you're trying to deploy a customer service bot, right, like in a company. And if you're doing that, the way to build an eval is take your real-world conversations, and that's your prompt set. That's the sample of the universe that you're starting with. And you take 1,000 or 2,000, whatever it is that you think is a good number of conversations that will give you a tight enough confidence interval. And you want to review each one of them carefully and write down this is a process of building, by the way. The one I'm talking through is an auto eval. If you wanted to do a human eval, it's much simpler. You can do two AIs and you can just have them talk to people and then people can just thumbs up and thumbs down. It's much easier to implement. The downside is it's much more expensive to run on an ongoing basis. So if you wanted to build an auto eval, what you would do is you would review all of these samples of 1,000 or so plus conversations, and you would write golden responses to them, like good responses. And now you can have different models answer the questions, the same set of questions, and you can compare the responses to your really good responses and make sure that they have the information that is needed in there and meet other criteria, whatever you may have. Once you've built the eval, which is, it takes some time to do that, but once you have built the eval, you have a process which can be run in a matter of hours on any new model that will give you a score of how good the model is. And you can run it with humans, and you can see human performance numbers. And this now gives you two very valuable tools. One is when your models are below or above human performance in a very clear mathematical way for your particular use case. And then second is it gives you a way to iterate on models, improve them. As you push that score up, the model will become better and better at the task that you're trying to do. So I think that's kind of like maybe one example of like how you would do it, but this generally you could apply to any situation. Anywhere where you're trying to deploy an AI system, you probably first want to start by building a clear eval and have a clear understanding of what it is going to mean for you to be better than humans at that task. Or if acceptable, maybe half as good, or whatever the goal is. It doesn't have to be necessarily better than humans. And so that's kind of like where things are in terms of eval. There's another example here, which I'm not going to go through. I will save the last 13 minutes or so for questions. I think your mic is off.
Okay.
And by the way, the questions don't have to be related to necessarily evals. That's just what I wanted to talk about today.
Thank you for your presentation. I have a question. How different are real-time conversational models from the normal models that you just presented? That's the question.
Sorry, what's the question?
Real-time conversational models.
Right.
Are they theoretically different?
Not really. I think, so what I talked about and the interpretation scheme that I talked about, which is here with the tokenizers and tokenization, generally applies to also things like image and speech, but in a very different kind of way. Not so much for image, where you will have the convolutional neural networks, you'll have the images put in directly oftentimes. But these days, even for image, the adapters that are being used are transformer style, which means you are tokenizing things. For speech, you absolutely do tokenize. Now, in terms of like the back and forth, nothing changes other than the fact that you actually are running inference more continuously. But there are modifications to the transformer architecture, but there is a meta paper actually from our FAIR team which removes the need for tokenizers altogether and trains them directly on the byte stream. It's a very promising research. My hope is that tokenizers will disappear in the future, but that's a hope. There's nothing that I know magical about it. They are a nuisance. But yeah, there's no critical sort of core difference in the architecture that is, yeah.
Okay, thank you.
I think we have.
Thanks a lot for the speech. I was curious, like some companies already open source their solutions, like Meta, like DeepSeek, and some stay closed source, like OpenAI and Twitter. Do you expect more companies in future to go open source, and do you expect it to be more popular to just run all of it locally? Of course, my mom not gonna do it, but maybe like more professional settings, like for developers, when like some companies would study it for like and just run it for their local knowledge base. And the second question I had, I seen Meta some time ago, at least in Instagram, they tried to start labeling generated generated content with AI. Do you expect anytime in the future we will have like a new Turing test or something like this?
Yeah. To your second question, I don't know if it's an answerable question by me. Well, Instagram. While I can't speak to Instagram's policy, I'm in the AI team, so I don't work in Instagram. I do know that they do that, and whether or not there's going to be a perfect test, my expectation is that's going to be very hard. There's going to. It's kind of a a game of it's an adversarial game. The better you get, the better other people get. It's same as spam, where people are very good at detecting spam, and then other people get even better at writing emails that are more spammy and can avoid the spam filters. To your first question on the open source, the general, at least my belief is generally that I think it will move in the direction of more open source as companies start to realize that sort of keeping the models closed isn't nearly as unique, or the models are becoming more commoditized. The research is out there. We're actually very happy with the way things are developing, from like feeling a little more vindicated and validated from like 2 years ago, where like the community is growing and people are taking llama models and building versions of llama models, which I don't think we had neither the expertise to do that or the imagination to do these things with these models that people have, the community has done, right? They take the models and they'll build like all kinds of crazy stuff with it, which is very cool. And it gives, personally to me, it gives a lot of joy, like, because I'll read something and I was like, oh wow, like I didn't even think about that, like, and I think I can tell you, like, nobody in our team would have thought of this, right? Like, and somebody just like does it. So I think specific applications in the future are going to be much more of that, much more of, I think we're back in the age of, if I think back, it's like, early days of the internet, where individuals had so much power because everything was like green territory, right? Like there was just like a lot of open territory for people to explore, and people would just go and do things by themselves, or a small group of people would go and build some cool stuff because there was all this technology and most of the world hadn't yet gone digital. And I think we're at similar place where most of the world hasn't yet gone artificial intelligence. A lot of systems are still like these old school systems. And with these models being open source, today I can take like a couple of gaming GPUs and train like, or fine tune, not necessarily train, but at least fine tune a small Llama 3 8B model in my house, right? And so if I had and 8B is a lot of parameters to do some specific task. If you have an idea of some wonderful task that you want to do, that nobody has thought of, which I'm sure there are now many, because we were just at the beginning of this. So I think that's what's going to happen. We are going to see many people doing this, and undoubtedly some of them will build large, very valuable enterprises, I'm sure, over time. But this is the age of like, hey, lots of stuff today is digital but not intelligent. And how do we take that? A simple example is like these days I go and I try to interact with anything online. Like I'm fumbling around menus on my, I don't know, banking app or like whatever, or I'm trying to figure out how to use a particular thing. And it just, the thought that occurs to me is like, why am I doing this? Like, why isn't this thing just, why am I not just allowed to just type in and say, hey, can you do this for me? Right? There's no real need for menus in almost any apps, actually. There's, you can eliminate all of them, but it's not going to be one AI that can eliminate all of them, right? Like it's the app maker, or maybe a new app will come around that will be inherently built with AI, where you will know your menus and your options and your things inherently so well, and it doesn't even have to be a big AI, right? Like you're just trying to know one application. And even 8 billion might be an overkill for that. A billion parameter model can know one application very well and just do it. So I think that's kind of the direction that open source will unlock and open in my mind. And I'm really looking forward to it because it's quite tiring to interact with things that are like really very, not very flexible.
More questions?
Yeah, I wanted to ask, do you think the future in AI is more towards general AI that can solve multiple types of questions, or towards multiple very specialized AI for each specific problem?
Yeah, I think when I think about, this is my view, different people, even in my team, have different views, so I think people differ in. I don't think we are getting anytime soon an AGI that is generally intelligent and can do everything, and I think that's not going to happen in the near term. I think what's going to happen is maybe the definition of AGI will transition a little bit to sort of the latter, where you have some AIs that are good at a wide variety of tasks, because we as humans do want to accomplish a wide variety of tasks in our day-to-day. But by and large, a large number of applications are going to be certainly smaller, purpose-built things that will just do whatever it is they need to do in their domain. And they don't really need to know everything else, because at that point, you're just trying to do that particular thing.
Hi, you're talking about context length when it comes to models, and I was curious why when we look at, for example, Google's Gemini models, they have the crazy big million token context models, but in open source models, we don't really see those high numbers.
Yeah.
Is it a goal, or is it not really a priority when you already have 150,000 token models?
Yeah, I mean, I think it's just a product of who is doing the open sourcing. Like, I think different companies have different priorities in what the models are useful to them. This is purely a speculation, but I imagine Google internally needs long context for something that they do in their business, and therefore they spend a lot of time and energy on it. I would think, like, the companies that do open source, like we probably don't need that much of a context, and we're not spending as much time and energy on it. So I think if Google was the company that was doing a lot of open sourcing, I would imagine open source models would have very long context because of that. Yeah.
So it's not really a goal of the Llama team necessarily.
Well, I can tell you it's not my goal right now to do it to 1 million. Yeah.
Okay. I also wanted to ask, if you don't mind, about when you as an open source team, when you look at companies like Grok, which are putting a big emphasis on uncensoring their models, even if it comes at the cost of being less politically correct and less biased, if that's a goal that the Llama team is looking at as well?
I don't know if I can get too much into that area, but I do know that like Grok, for example, spends a lot of their time and energy on inference optimality. And we partner with them on like, hey, increasing inference speed for Llama models, and so that like a lot of people can use the models and do it. But there are many players that take the models and they're like sort of uncensoring them and stuff like that. That is just the nature of like being open source. It's just part and parcel of people are going to do things with it, and you just kind of have to know that going in. That once you give something to people, it's there to take and do whatever it is that they want to do, and they will do wonderful things, and they will do other things that maybe you weren't going to do. So yeah.
Sorry, I wasn't specific. I meant the Twitter Grok.
Got it. Yeah. I guess it's like a personal choice that they make as a company. I don't know that. I don't really have much insights into their decision making to comment on that really.
But do you think the Llama models are biased in comparison to other models?
I think our models are the best models, but yeah.
Yeah, thank you.
Hi. Lately, AI agents and multiple agent architectures are becoming really trendy. Do you think that that will be the future of these kind of solutions? And how do these methods that you showed us for evaluating performance, how can they be applied to those more complex architectures with multiple AIs working together?
Yeah, that is an excellent question. And I think the answer to the first part is absolutely. I am spending a ton of my own time on agents. I think agents started as people trying to orchestrate models to do some things that they weren't going to do by themselves, right? So you can put some structure around it, and you can use this sort of kernel of intelligence that the model has. And then you can take that kernel, and then you can orchestrate and make the model do things, more complicated things that there was. Now the situation is that you can actually fine-tune the models to be very good at these agentic things. So you can achieve a lot more through these orchestrations. We are spending time on sort of like training models that will be very good at it being agentic natively, which wasn't the original goal, right, like of any of the labs. So I think that's here to stay. In fact, that is we will probably move from a pure LLM view to like a sort of like a system level thinking where everything is just going to be like a whole system, and it might be like a combination of models in the background that are working to do something. In terms of evals for agents, it's a very complicated area. I think it really substantially increases the complexity of evaluation. The reason that happens is because it substantially increases the complexity of things that the AI can do. Now, like, it's a language model, and you can see that I have these tokens on the right hand. It can give you this output. But now you can shape this to make it do a lot of different things. You can make it navigate the internet, or you can make it sort of like operate machinery and all kinds of like other things. Send emails, receive emails, read your emails, messages, and fetch your insurance cards and all kinds of things, book reservations. As the space of things it can do expands, to evaluate them, you have to create this virtual world simulations in a way to be able to see if the model is doing the right thing, because it's not enough to just take the answer and compare it to some other answer, right? And that obviously increases the complexity, but that is the way to do it. The way to do it is to create simulations of the worlds and then have the model operate in those simulations, and then you test it. Yeah.
Thank you.
Okay, so now we'll pick the winner of this session. And then Rohit will go to the second stage if anyone has more questions.
Thank you, everyone.
So the winner is Pedro Curto. Obrigado. Ai, cuidado. Isto é muita espécie.